Here then is the solutions. We go through them and see if you have any questions. I thought this is a fairly comprehensive test. It tested the things you really need to know out of this chapter. And I think if you did well on this test, you're probably a pretty good trig student when you get out of here, even if you don't learn the rest of the course. Beginning today and for a while, we're going to, the next maybe week and a half, we're going to finish the trigonometry. How about that? We're going to do the solving oblique triangles. Those are triangles that don't have a right angle. But those problems are actually some of the least important out of the course. What we need to be able to do is solve triangles, which isn't on here, but I think if you can do this, you'd probably do that. And do what we did here, the identities and the unit circle and the solving equations and simplifying expressions and solving these trig equations with the various techniques. These are the things you need to be able to do in calculus together with the solving triangles and other higher courses, your science courses, your first year physics course you need. This is what you need out of trigonometry. So if you did well on this one, I think you'll be a good student in the future whenever you need trig. Here's the first problem, and I think you'll see this is fairly comprehensive. Because it was kind of comprehensive, it was fairly difficult. I'm going to give you an easy curve on this. We'll say 80 to 100 is an A, 60 to 79 is a B, 40 to 59 is a C, 20 to 39 is a D, and 0 to 19 is an F. So it's 20 points per grade level instead of 10. That's a very easy curve. So just because it's a slightly harder test. But if you're struggling on, come by and see me in my office hours. I'd be glad to go through all the things with you. All right. So here's the first problem then. Let's see. We want to find the exact value of the sine of 13 pi over 8. And I gave you a hint, use a half angle identity. Why did I say that? Because 13 pi over 8 is 1/2 of 13 pi over 4, a special angle, right? The special angles are multiples of pi over 4 or pi over 6. 13 pi over 4 is a multiple of pi over 4. So I know that this angle here, 13 pi over 8, is half of a special angle, 13 pi over 4. So I use the half angle identity, right? This is sine of 1/2, 13 pi over 4. And the sine of half an angle is plus or minus the square root 1 minus the cosine of the whole angle over 2, right? Now, the whole angle, 13 pi over 4 is special. I can figure it on the unit circle. So that's what I did. But first I'm going to say, is it plus or minus? You don't go by the quadrant of 13 pi over 4. You go by the quadrant of the original angle, right? The square root means the non-negative number that has the square. So it's positive here, right? And so if this sign is supposed to be negative, I'll put minus here. If this sign is supposed to be positive, I'll put plus here. This original angle, 13 pi over 8, if I counted 8 pi over 8 and 5 more pi over 8, puts me in quadrant 4, right? And if it's a quadrant 4, you recall that the sign is negative, right? The y-coordinate quadrant 4 is negative. So I'm going to put minus here. Now I'll say cosine of 13 pi over 4. I'm figuring on the unit circle, and this is a good test of unit circle. Where's 13 pi over 4? Well, 2 pi is 8 pi over 4. Then another pi is 4 pi over 4 more. That's 12 pi over 4. And 13 pi over 4, another pi over 4, 45 degrees past the negative y-axis, right? I go around at 1.5 and then another 1.5 rotations and then another 45 degrees past there. So now I drop the perpendicular. It's a 45, 45, 90 triangle. So the coordinates are minus square root 2 over 2 minus square root 2 over 2. It follows the cosine is minus square root 2 over 2. And I put it in here. Now that's 2 points off, I think, is what I gave if you get to there, because it's an exact answer, but you've got compound quotients and this thing simplifies, right? So I'll multiply top and bottom by 2 to clear out this denominator of 2 here in the compound quotient. And then 2 times 1 is 2, 2 times this is square root 2, and the minuses cancel. And then on the bottom, I have 4, right? 2 times 2. So I multiply top and bottom by 2, so I don't change the quotient. I get this. Now I got rid of my compound quotients. The square root 4 is 2, so I'll write the quotient. The square root of the quotient is the quotient of square roots, and right square root of 4 is 2. Now that's far enough. Sometimes these things simplify. I didn't ask you to see if that's simplified or not. All right, so this was a good answer right here. An exact answer. If you put a decimal, it's not exact, because this goes on forever without a repeating pattern like pi. So wherever you round it, it'd be wrong if you round it. Okay. Any questions on that one? Ask questions online also as we go along. Feel free to. Here's another one. Solve a trig equation exactly where its trig function equal a number, right? And I gave you the tricky case. What if it's not sine, cosine, or tangent, the ones we usually solve, but secant, cosecant, or cotangent? Secant 2 theta equals minus 2 over square root of 3. Remember, if you see a secant or cosecant, immediately write the reciprocal. Cosine 2 theta equals minus square root, minus reciprocal of this one, cosine 2 theta is reciprocal of this one, minus square root of 3 over 2. Aha. Now we said when you have one of those three cases, sine, cosine, or tangent of an angle equals the trig function, you get a single angle. You don't leave this double angle. You substitute u equals 2 theta and write cosine. U equals minus square root of 3 over 2. Because then I can solve it on the unit circle. All right? So get cosine of a single angle equals a number, and you can solve it on the unit circle. That's what we did. On the unit circle, cosine is the x coordinate. So I'll draw the vertical line, x equals that number, minus square root of 3 over 2. It's close to -1, so it's over here. You kind of draw it over close to -1. And then you say, well, there's 2 points in the unit circle that have that x coordinate, so only 2 terminal rays can lead to this cosine. Right? Those two. And what are those angles? Well, I noticed it was square root of 3 over 2 units this way to get to the line. So this side of the reference triangle here must be square root of 3 over 2. This is 1 because it's a unit circle. Oh, it's a 30, 60, 90 triangle, right? Pythagorean theorem will make that at half. This must be a 30-degree angle, pi over 6. Right? Now, if that's a 30-degree angle, then this is also a 30-degree angle by symmetry, right? It's the same triangle over here because that's the same base and the same hypotenuse. They're both right triangles. So now I know what the angles are, right? To get to this one, I take pi back up pi over 6. That's 5 pi over 6. To get to this one, I take pi and go forward pi over 6. That's 7 pi over 6. So you can be 5 pi over 6 or 7 pi over 6 within one rotation. Right? But now all angles u that can get me there, I can have any coterminal angle. There's an infinite number of them. So I add k rotations, any integer k, right? 0, 1, minus 1, 2, minus 2, any number, any whole, plus or minus any whole rotations, right? So 2 pi is one rotation, 2k pi is k rotations. So I can take 5 pi over 6, this angle, plus one rotation, 2 rotations, or this one plus minus a rotation, minus 2 rotations. Infinite number of choices, 2k pi. These are all the coterminal angles to 5 pi over 6, where k is any integer. And these are all the coterminal angles to 7 pi over 6, this one. So these are all solutions for u that you can possibly have, all angles that have these term rays. But now we were asked to solve for theta, not u. So we remember that u equals 2 theta. We say 2 theta is this, or 2 theta is this, is all solutions theta. And then we can divide by 2 to get theta, right? Divide the whole side by 2. 5 pi over 6 is 5 pi over 12. 2k pi divided by 2 is 2k pi. Same thing here. 7 pi over 6 becomes 7 pi over 12. 2k pi becomes k pi. These are all angles theta that will make u be one of these two angles. So those are all the solutions theta, except we said we only want theta within one rotation. So now we have to go back and say these aren't all within one rotation. Let's throw out the extras. So theta between 0 and 2 pi, we just dig in different values of k. If you put k equals 0, you get 5 pi over 12. That's between 0 and 2 pi. K equals 1 gives this plus pi is 17 pi over 12. If you put k equals 2, it's 2 pi plus a positive number is too big. You put k equals minus 1, you get a negative angle, it's too small. Same thing over here. K equals 0 and 1 gives you these two angles. Anything bigger or smaller gives you something bigger than 2 pi or less than 0. So these are the only 4 angles within one rotation that will make secant 2 theta equals minus 2 over square root of 3. 4 answers. How about that? So I give you partial credit on all of these. If you got, this one and don't put that one, I'll give you more than half credit actually. Let's go on to the next one. Suppose I want to solve this trig equation. It's not just trig function equal a number this time. It's number times the trig function squared plus the number times the trig function plus a number equals 0. How do I solve that? Remember, if it's a trig squared plus b trig plus c equals 0, you substitute u equal the trig function. It turns out it's a 2u squared minus u minus 1 equals 0, a quadratic equation in u, right? Which we know how to solve. We can apply the quadratic formula immediately, or a lot of times when it's so simple like this, it's easier to factor. So I just factored. I look at it and I say, wait, that factors from algebra as 2u plus 1 times u minus 1 equals 0. Factoring the left with the right side 0 allows me to use the zero product property. This product is 0 if and only if either this factor is 0 or this factor is 0. So either 2u plus 1 equals 0, which means u is minus a half, or u minus 1 equals 0, which means u equals 1. Those are the only possibilities for you to satisfy that equation. Two solutions for u. But u is sine theta, so sine theta equals minus a half or sine theta equals 1. Some people got there and then had trouble finishing. I was surprised. I thought this was the hard part, but maybe not. Now, when you have trig function equal number, go to the unit circle, just like we did in the first problem, right? But this time it's a single angle, so we don't need to find all angles and then throw out the extras. We just have to solve it within one rotation. So sine theta equals 1/2. Sine is the y coordinate. I give you the x coordinate in the first problem. Now I give you the y coordinate. Y equals a number is a horizontal line, right? Here's all the points. Y equals 1/2, halfway between the 0 and -1 at the bottom of the circle. And so I observe that there's 2 points on the unit circle without y coordinate, and therefore 2 terminal rays here. What are those angles? Well, I went down half a unit here, so I make this right triangle. It's half a unit down and 1 unit on the unit circle. Oh, this is 1/2 1 must be square root 3/2 by the Pythagorean theorem. That's a 30-degree angle, it's pi/6. And by symmetry, this one also must be pi/6. It also went. So there's the angle, 7 pi/6, pi plus pi/6, and 2 pi back up pi/6 is 11 pi/6. That's right, 7 pi/6 and 11 pi/6. I didn't mark the other one. Oh, they have to run enough room, so I didn't mark it. 7 pi/6 and 11 pi/6. That's these two solutions. And then what's the last one? Sine equals 1. Well, that's y coordinate equal 1. There's only 1 point. This is tangent to the unit circle because it only goes up 1 unit. 1 point on the unit circle with y equals 1. That's at this angle here, pi/2. So that's the last solution. 3 solutions out of these 2 equations. And you don't need to put plus 2k pi and throw it out because we didn't have to put, it wasn't a multiple angle here. We just wanted all angles within one rotation. We don't have to go back and find all angles and then throw the others out. We just do everything within one rotation. Okay, everybody happy with that one? Not getting any questions yet. I guess it was so easy, huh? I give too easy a grade curve. Let's see. That's one of them. Where'd my other 2 go? I had the other 2 pages up. I guess I can get it back. Here's page 2. Oh, there it is. I see it. I clicked on it before. All right, page 2 comes back like this. Simplify using the half angle identity. Square root 1 plus cosine 200 degrees over 2. That is half angle identity. What is that in the half angle identity? I remember cosine of half an angle is square root 1 plus or minus the square root 1 plus cosine the whole angle over 2, right? Well, if cosine half angle is plus or minus the square root, then the square root must be plus or minus cosine of half the angle, half of 200 degrees. That's our half angle identity. What is it plus or minus? I just put the plus or minus on the other side of the usual identity. The side is true. Well, the square root, remember, means the non-negative number that has the square, and this isn't going to be 0, so this is a positive number. So I need a positive number on this side to match, and so I say, well, cosine of 1/2 200 degrees is cosine of 100 degrees. That's in quadrant 2, where cosine is negative. If cosine of 100 degrees is negative, I put a minus in front to get a positive number on this side to match the positive here. So I want minus cosine of 100 degrees. Some people missed the minus there. Told you this exam was tricky, right? So I want minus cosine of 100 degrees, you get plus the square root, since cosine is negative in quadrant 2. All right, here's the next one then. Solve the trigonometric equation again for theta between 0 and 2 pi, but this time approximately, because this is what happens in real life mostly. If you're out in the field measuring in your farm or something, you get tangent 4 plus 1 equals 0 from your measurement, and what angles satisfy that, I wonder, between 0 and 2 pi? is not a special angle, right? What angle has tangent equal minus a fourth, right? You solve this algebraically by subtracting 1 and dividing by 4. You get tangent theta is minus a fourth, which tangent is y over x, right? So I give you sine, I give you cosine, now I give you tangent is minus a fourth. How do I solve that? One solution is always the inverse tangent, right? Theta could be the arc tangent of minus a fourth. So I drew that over here. When you draw it, this is sometimes an advantage. Remember, arc tangent of a negative number is negative. Arc tangent is between plus and minus 90 degrees. Negative if you put in a negative number, positive if you put a positive number. So arc tangent negative a fourth is actually in quadrant 4 over here. It's not between 0 and 2 pi. That's not one of the answers. But I realize also that whenever y over x is a quotient like that, here's the y coordinate to the x, the opposite direction is the only other direction, I should say, that it has the same tangent, right? Over here, if you put x negative, the same measure, and y positive with the same length, then again, y over x is the same quotient. And that's the only way to make y over x the same quotient, minus a fourth, is to put the opposite direction here. So arc tangent minus a fourth gives you an angle, but not positive. And arc tangent minus a fourth plus pi, the opposite angle, also gives you the same tangent as minus a fourth. So what we want for the answer for angles within one rotation, instead of taking arc tangent, we'll take arc tangent plus a rotation, gives you this angle here, right? And so arc tangent minus a fourth plus 2 pi is one solution. That's this one. This angle right here. And the other one is arc tangent minus a fourth plus pi. That's this measure here, right? The opposite one. So those two are the exact measures, but I actually define it approximately, like you're actually going to measure out in your backyard or your business or something. So you run out on the calculator, and you find out with your calculator in radians mode. Why is it so important you put radians in this problem? Besides that, I asked for radians when I said between 0 and 2 pi, that means use radians. Well, because if I'm going to add pi in radians, I better put a measure in radians here. I'll be adding partly in degrees and partly in radians, right? So if you put your calculator in radians mode and add arc tangent minus a fourth plus pi, you get 2.89661 and a bunch of other digits. And I said round to 2 decimal places. So you put 2.89, the next digit is 5 or greater. So you round this up to 2.90. You must put that last digit, or people assume you rounded it to 1 decimal place, right? So this is a significant digit. You have to write the 0. Similar over here, 6.038, blah, blah, blah. The next digit you don't want is 8, so you round up to 6.04. Those are the 2 answers I was looking for there. Correctly rounded at 2 decimal places, 2 places after the decimal point. Now simplifying, right? These are tricky. Sine squared minus 1 all times secant squared. How does that reduce? There's a lot of ways to do this, and you can accept all of them, but one thing to think of is, wait a minute, if it was 1 minus sine squared, that would be cosine squared. I could reduce it, right? So I write this as negative of 1 minus sine squared. So this is minus 1 is that one. Minus is plus sine squared. It's the same thing. And 1 minus sine squared can then be replaced with cosine squared, right? So minus cosine squared times what's left secant squared simplifies it a little, right? I got rid of that 1. And now I recognize, wait a minute, secant squared is the reciprocal of cosine squared. 1 over cosine squared will cancel this cosine squared, and I'm left with minus 1. All this messy expression just is minus 1. How about that? It's a constant. Who would guess with that theta in there that can be anything, that this is always minus 1 regardless of what angle you put in, right? But it is. There's the proof. Right? So it simplifies to negative 1. Don't give this to your boss at work when the answer is negative 1, right? So, all right. Here's the next one. The object on this one say, what does that look like? What does that look like? I know 2 tangent theta over 1 minus tangent squared theta is a double angle identity, right? It's tangent of 2 theta. If only I have a 2 there, right? So I'll put it there. I'll multiply by 2 and divide by 2. That is multiply by half to cancel it. Now this is equal, right? Because these cancel if I want. But 2 tangent of 15 over 1 minus tangent squared 15 by the double angle identity is equal to tangent of twice 15. So I have 1/2 tangent twice 15. Some people missed this 1/2. They forgot there's a 2 up here for the identity. Or 1/2 tangent 30 degrees, but 30 degrees is a special angle. I figured on a triangle, right? 30-degree angle. I've got 1/2 square root 3 over 2 and 1. The tangent is opposite over adjacent. This over this is 1 over square root 3. So I'll replace tangent 30 degrees with 1 over square root 3. This is a good answer. I accept that as full credit. If you rationalize it by multiplying top and bottom by square root 3, you get square root 3 over 6. I wrote the answer that way for the test. But this answer is good too. Finally, on this page, once again, what does that look like? See on 50, all your identities, cosine, cosine, plus sine, sine. That looks like a summit identity, right? We did a half angle and double angle identities here. Let's do a sum of the angles. Cosine, if it was cosine alpha, cosine beta, plus sine alpha, sine beta, I would use the sum of angles identity. But wait, it's beta alpha. It doesn't matter. The sines can multiply in either order. This is same as cosine 5x, cosine 2x, sine 5x, sine 2x multiplied in the other order. So this is this difference identity. I call this sum, didn't I? Cosine, cosine plus sine, sine is cosine of the difference of the angles. Alpha minus beta, 5x minus 2x, which is cosine 3x. I want to simplify it as far as possible, right? So that complicated expression there is just a single wave, right? Cosine 3x with period 2 pi over 3. It's easy to draw and see what it looks like now, right? All right, here's the last page of proof. All right, establish the identity. I used to solve these when I was early on teaching this stuff many different ways, and you can do your proofs many different ways. They do work as long as you prove it. I used to write this one and then try and work on each side, writing the equation over and over until I got them to match. And as years went by, I realized, why do I want to write both sides all the way down when I don't have to? And there's other ways to do this too. Some of you did creative things with arrows going around the page, and I had to figure it out. It was very fun. It's spaghetti math is what it is. Anyway, I like to do this. It's very clean and straightforward, right? The left side here and the right side here. I'm trying to make the two ends meet, like we said in class, right? So whenever I see more than 2 trig functions in here, I just, as a rule of thumb, like to convert it all to sines and cosines. It usually makes it easier, right? So I've got 4 different trig functions here. I'm going to convert it, right? So I'll write tangent is sine over cosine, cotangent is cosine over sine. And then this one I'll write as 1 over sine, and this one is 1 over cosine, and their product then is 1 over sine times cosine. So I go both ends towards the middle, right? And I get that. Now, how can I make these two meet? There were 3 rules you had, right? Besides just getting one angle, and it already starts with one angle. If you had a double angle, you fix it first. You rewrite it in terms of all sines and cosines if you want to, because it sometimes helps. Then you use algebra rules and you use trig identity. So what's another one? Oh, look, 2 sums with different denominators. What do you do in algebra? You put them over a common denominator, right? That's how you simplify. So I'll do that. Multiply this top and bottom by sine, and this one top and bottom by cosine, each one by the other's denominator to make them have the same denominator. Then I get sine squared over sine cosine and cosine squared over sine cosine, the same denominator, so I can add them. Sum of the numerators, sine squared plus cosine squared over the common denominator, sine cosine. There it is. Sine squared plus cosine squared is 1. All right, so now you apply your trig identity. We used all 3 steps here once. Right, in terms of sine and cosine, use some algebra tricks, and then apply a trig identity. Sine squared plus cosine squared is 1. And now I recognize, wait a minute, I just made the 2 ends meet. There it is. So this is a nice, clean way to do it, but I took whatever spaghetti math or creative method you use as long as I can figure it out. All right. Any questions on that one? I'll look around. Let's try the last one then. It wasn't too long a test, right? I said one of the things you want to be able to do for this test is given a trig function and a quadrant, you want to be able to find all the trig functions of the double angle and the half angle. And it works because given a trig function and quadrant, you know all the trig functions of that angle. And then once you know those, you use the double and half angle identities to find trig functions of double and half angles, right? So this is one of those classic problems you see in every trigonometry book. What I do is I say, if I know sine, I immediately know cosine. It's plus or minus the square root of 1 minus sine squared. Is it plus or minus though? Quadrant 4, in quadrant 4, cosine is positive. So I didn't write it here, but you use positive here because it's in quadrant 4, where cosine is positive. Now sine was minus 3/5, so it's 1 minus a negative 3/5 squared. Since you square it, the minus goes away. Then you've got 1 minus 9/25. To reduce that, you get a common denominator. 1 is 25/25. Then you subtract the 9/25, you get 16/25, which is a square, right? 16 is the square of 4, 25 is the square of 5. So the square root of 16/25 is 4/5. There's the cosine. And if you haven't figured it out, what I've essentially done here is giving you a 3, 4, 5 right triangle. Maybe I should move this over. I know some of you did this. You look in the book and they like to do this kind of thing. And this is a good technique that I haven't emphasized so much in class, but you can do this. When you say sine is minus 3/5, you can go down 3 tick marks of 1/5 each and say there's minus 3/5. I found that cosine, I find that we're in quadrant 4, so we're over here. Right? So I want to be on this terminal ray with sine equal minus 3/5. Here's cosine on the x-axis, right? And what you can do is say, well, if this is on the unit circle, so the hypotenuse is 1, and this is 3/5 on this side because I went down to negative 3/5. You can find this, you can say, oh, this side is obviously positive. This by the right triangle is square root of hypotenuse squared minus the other leg squared, you can put plus 3/5 squared. Gives you 4/5, and that tells you this one is 4/5 here. So some people like to draw it in the unit circle, and that's a good way to do it too. And once you have that, then you can find cosine of 2 theta was the original problem, right? Let's move this back. Then use your double angle identity, right? Cosine of 2 theta is cosine squared theta minus sine squared theta. Is 4/5 squared minus a negative 3/5 squared, 16/25 minus 9/25 is 7/25. That was it. All right. And it'll look easier now. Much looks easier after sitting back. That's the object. If you can do this stuff getting out of here, I think you'll do well in your calculus class. Or whatever other classes it's for. Okay. Let's close that out. Now, I think this will be a fun day today. How about this problem? Today, we're going to start doing some interesting applications of trig. And this is really the last big trig topic for the course, but it's going to take us a while. Is solving oblique triangles. What's an oblique triangle? We sort of said it at the beginning. Or I said it once at the beginning. An oblique triangle is a non-right triangle. Anything but a right triangle. Any triangle but a right one. And so here's an interesting case. Suppose you went over to the Leaning Tower of Pisa and you knew from the specifications it's 56 meters tall. And you stood from the center, walked out 25 meters this way, paced it out, and then took out your sextant or protractor or something and measured the angle up to the top and found it 73 degrees to the middle of the top. You can figure out how to solve this whole triangle, it turns out. This is not a right triangle, right? The left tower of Pisa isn't pointing straight up. So you can't use right triangle trigonometry, which is the most important we've done. We're going to have to solve a non-right triangle. And that leads into today's discussion here. So the topic now is solving oblique triangles. And we'll just repeat. Oblique triangles are non-right triangles. No right angle. We can solve an oblique triangle using one of two methods quickly. Or we can do it a long thing. I wanted to point out just in passing that I find a lot of people get out trigonometry and they can't remember this last part of the course on oblique triangles, but they can still solve this thing. A lot of engineers seem to do this. We can solve these already with difficulty. So this is worth saying because you might forget this last part too. It's like people get an algebra, never remember logarithms until they go use them. And the same thing happens here. Until you go do oblique triangles, you tend to forget this stuff sometimes. So we'll say we can solve them already with difficulty. For instance, suppose I'm given this triangle here, which is not a right triangle. And suppose I happen to know this side measure is 15 meters. And this angle here is 40 degrees. And this angle here is 30 degrees. Let's see. Yeah. So I know an angle followed by an angle followed by a side in order, right? Rotating around angle, angle, side. Data given. What do you know from geometry about angle, angle, side data? That completely determines the triangle, right? There's a congruence term. Angle, angle, side is a congruence term. Any triangle with this angle followed by this angle followed by this side is congruent. It has all 6 measures the same. So I know the triangle is completely determined. How do I solve it? Here's the way that we can already do it. We could drop a perpendicular right here, right? And we could say, wait a minute, given an angle and a side, I remember in a right triangle, I can solve the whole triangle. So for instance, I can use right triangle trigonometry. Sine of 30 degrees is this over this, and figure out this must be 7.5, right? 1/2, so the ratio is 1/2 to 1, sine of 30 degrees being a half. And then once I know this is 7.5, I have an angle and a side over here, I can solve this right triangle. So you can do that with difficulty. And some of the cases are harder than this. I present this as an easy case. But you'll see engineers do it, and I'll say, if you forget all this stuff, then you can always drop a perpendicular and solve non-right triangles, right? To make multiple right triangles by dropping perpendiculars. However, there's a faster way that people really use in practice, because people who use this often don't want to drop perpendiculars everywhere and figure out all the different cases. So, however, there is a faster way. Faster, easier method. And it's pretty easy to memorize too. And there's actually 2 methods when you cover all triangles. There's another method for this one. There's another method for other triangles. Let's say faster, easier pair of methods for oblique triangles in general. And we say this, method 1 is called the law of sines. And I'll tell you before we get started, again, what I'm doing is trying to present the picture on the model box before we start gluing all the little parts of the model together so we know where we're going. It makes it so much clearer what we're doing, right? So the law of sines, this applies to triangles where you're given something like this, angle followed by side. That's a congruence theorem in geometry. There's only one such triangle. The law of sines will always find it. We'll solve all the angles and sides given, just the two angles followed by a side. Also, if you get angle, side, angle, that's a congruence theorem from geometry, right? We should be able to solve that. We can with the law of sines, it turns out. It's very easy. It's just a little harder to remember than the right triangle stuff. Finally, side, angle. Maybe you remember something out of geometry for that. That's not a congruence theorem, unfortunately. Nonetheless, even though it's not a congruence theorem, it doesn't uniquely determine the triangle. It almost determines the triangle. In this case, this is the bad case. There's an ambiguous case where there can be 2 different triangles, or there can be no triangles, or there can be 1. So this has 0, 1, or 2 solutions, depending. So it's not quite a congruence theorem, but you can find if there's no solution, or if one solution what it is, or if there's 2 solutions what they both are. So those 3 cases you can use the law of sines, and it always works. It always finds all possible triangles. The second case is the law of cosines. This one is according to books, you'll see every book says this that I know of. For side angle side data given, that's a congruence theorem in geometry, right? If you know side and two sides with an angle in between them, then the triangle is determined, completely determined. Sometimes I try and talk too fast on it. Or if you're given side data, who can remember all this thing? Even when I started teaching this stuff, I couldn't remember which one goes up. So I just kind of put these in and see which one worked. And that actually works. You don't have to memorize these two. If you use the wrong one, you'll get an equation with two unknowns. You'll say, wait a minute, I should have used the other one. So don't worry about this too much. But here's how I managed to learn it. Like this. If you have side angle side or side, that's law of cosines. And everything else is law of sines. Except there's one case left out. What is it? Yeah, awesome. Angle. We don't do that one because it's not a congruence theorem, right? And it's not a 0, 1, or 2 solutions. It's an infinite number of cases, right? What happens in practice is if you know two angles, alpha and beta, you already know the last angle, right? It's 180 minus alpha minus beta. So in some sense, angle is only two pieces of information, the third one being automatic. And you can't solve for a unique triangle. Remember, these are two triangles with three angles. The same three angles are called similar, and there's an infinite number of cases. You make the triangle with all the sides twice as long, or 3 times as long, or 2.7 times as long. There's an infinite number of solutions. This one has infinitely many. Sideways 8 means infinity. Infinitely many solutions. So we don't try to solve. Angle cases. We just say these triangles are similar, and we can say find their same ratios from two triangles, but that's all we're going to do. But all the other cases are solvable, right? There's actually only 6 different ways of arranging these things. So we're going to do that. Today we're going to do the law of sines. We won't quite finish. And then next time we'll do the law of cosines, then you'll be able to solve any oblique triangle. Right? So is the model box complete? We're building all the oblique triangles model. And angle, we won't do because it has infinitely many solutions. All right. Here's the law of sines. The proof is not short and it's not illustrative, so I'm not going to do it, but you can look in the book and see it. It's not out of your ability to do it, but I like to do the ones that, you can remember them and figure out the theorem, and then you forget it kind of thing. And this one is just not one of those. So the law of sines is this simple. It's very simple. In any triangle, including right triangles, this applies to right triangles, but can you guess why we don't use it for solving right triangles? Yeah, but the other way we already learned is easier. This will work. I'll show you as we go along sometime, probably next time or so. But it's easier just to use the right triangle trig we already did. So, you can certainly use this one if you want. It's just one more step. In any triangle, and here's an arbitrary triangle, which could be a right triangle, but just any triangle, you can label the angles however you want. It's not like the convention in right triangles where a hypotenuse is C. There is no hypotenuse here because it's not a right triangle. And we'll just label the angles however we want. Alpha, beta, gamma. And then opposite alpha, I put A, opposite beta, I put B, and opposite gamma, I put C, even though gamma is not the third letter of the Greek alphabet. And by the way, if those don't look like Greek letters, these are the small Greek letters, like gamma on the Greek houses looks like that. This is capital gamma, this is little gamma. So in any triangle, not necessarily a right triangle, if we draw it that way, so A is opposite alpha, B opposite beta, and get C opposite gamma, then it follows that the sine of alpha is to A, as the sine of beta is to B, as the sine of gamma is to C. There it is. There's our superstar equation for today. It's the only new one we're going to do. How about that? It's that simple to write down. The sine of each angle is to its opposite side as the sine of any other angle is to its opposite side. And this is really three equations written succinctly here, right? You can have this equals this is one equation, this equals this is another, and this equals this is another. It's really three equations, and you pick the one that you like best for the problem. All right. Now, back to the problem we had. Suppose I go visit the Leaning Tower of Pisa, and I get this oblique triangle. What have I got here? I've got a side, followed by a side, followed by an angle rotating around this way. Don't rotate the other way, you get a bad word, right? But side angle is the bad case, literally. It's the one that's not a congruence theorem. You can't get 0, 1, or 2 solutions. But if we also know that this angle is between 0 and 90, then we can solve this immediately using the law of sines, right? So side angle is the law of sines. We can solve this, even though it's the bad case. Here's what we do. Uh-oh. I just hope you know which way is right and which way is left. All right. So example, the Leaning Tower of Pisa. An applied problem, right? All these problems in this section are going to be applied. It's very cool like that. It's very fun to see what you can solve. And suppose we measure, and by the way, on all these problems, I think it's a wise idea to draw the picture. It helps you catch mistakes, and it often gives you intuition for how to solve these things. So here's what we have with the tower. The specs say it's 56 meters tall, from the center of the bottom to the center of the top. I measured off pacing 25 meters this way, and then I measured up 73 degrees to the middle of the top in that picture. I wonder what angle the Leaning Tower tilts at. I wonder what angle, let's call that theta, this is. What angle could theta be? Well, that's not even in the triangle. This is where the picture shines, right? The way I can solve theta is I can say, well, I really want to find this. I can find this angle, then I know theta. This one, if I call this whatever alpha, I can call it whatever I want, alpha, beta, or gamma. Then the object just find alpha, and then I'll know that theta is just, since these are complementary angles, 90 minus alpha. So I'm thinking I need to solve for theta. But wait a minute, I have side, angle in that order. Side followed by angle. And my rule there says since it's not side, or side, angle, side, it must be the law of sines. So I try that first. If I remember my rule right, I'll get it in the first try here. The law of sines, what I want to do is relate 3 items I know and 1 I don't, using one of those 3 rules. Star, right? We'll say by star, I know that, and here's the trick. You take an angle and an opposite side when you know both. All right, sine 73 degrees is to its opposite side 56 meters, let's write 56, as I need another angle in its opposite side. Well, all I have is this other angle, so I'll say sine alpha. I'm sorry, let's see. I have this other side here, sorry. This one, I'll call this beta. If this is gamma, maybe, and this is alpha, and this is beta, I'll label those 3. Sine beta is to 25. That's the only thing I can solve for with the law of sines. So I'll just solve for what I can, even though I don't need beta, I need alpha, right? So I'll solve what I can solve for. And now what I've done is write it so I have the 3 numbers I know, 73 degrees, 56 meters, and 25 meters, and 1 I don't know, I can solve for it. That tells me I use the right rule. There's only one thing I need to solve for. The other rule would apply. If I apply the law of cosines, I'll get a trig equation that relates 2 unknowns. And if I write 2 of those, I can get 2 equations and 2 unknowns and eventually solve it. The law of cosines also applies to all right triangles. But if you use it for this, you'll have to solve 2 equations, 2 unknowns. It's a mess. It's easier to drop a perpendicular, right? So what I'm going to do on these is say use the law of sines, and it's easiest. Now, once you have this, all you need to do is multiply by 25 to isolate sine beta, right? Sine beta is then 25 times this side is 25 sine 73 degrees divided by 56, right? And now I know it, right? Because what's beta? For beta acute, acute means between 0 and 90 degrees. And by the way, we're going to do practically all these problems in degrees because the idea is radians is real good for calculus. It makes all your calculus formulas easier and also in applied physics and so forth. But when you're actually out in the field measuring, like you're doing the tower, you want to know degrees. Who wants to say it's pi over 7 radians? How much is that? I can't figure, but if you tell me so many degrees, then I can picture it better, right? So we'll do degrees here with the idea you're a surveyor or something out in the field, and you want to be able to have an idea by looking at it, how far it is. Use whole number for right angle. So for an acute angle, we know immediately then by taking the inverse sine of both sides that beta is the inverse sine of 25 times sine 73 degrees all over 56. There it is. How do I know it's acute? Because it's this angle up here. The power's leaning this way, and this, and that makes this an acute angle, right? All right. Now, what is this? I run to the calculator. Make sure your calculator is in degrees mode. So since I did this in degrees, I have to do this one in degrees. Degrees mode. Let's try it. We will list this in degrees mode. All right. Inverse sine, remember how to do this from the last section, push second sine of 25 times sine 73, close the parentheses, divided by, divided by 56. And I get 25.27, etc. degrees. Where should I round that? When you're out in the field, rounding becomes important, and we don't usually use round to so many decimal places. We usually use round to so many significant digits, which is different. If these are rounded numbers here, then what you do is you start with the leftmost non-zero digit, and you say 1, 2. This has 2 significant digits. 1, 2. That has 2 significant digits. 1, 2. That has 2 significant digits. If I gave you 0.00127, how many significant digits in that if that's a correctly rounded number? There's 3 digits, right? You start with the first non-zero digit, count 1, 2, 3. 3 significant digits. If I gave you this number, 44,000, how many significant digits there? This is the one ambiguous case for rounding. Could be 2. I could have rounded to the nearest 1,000, or it could be I rounded to the nearest 100, and this one happened to be 0. Or the nearest 10, this one happens to be 0, or the nearest 1. You have to tell me when they're trailing zeros before the decimal point. But if there's zeros after the decimal point, it's just count from the first non-zero digits. Here's 3 digits, 3 significant digits, 5 decimal places. But this one, you have to tell me rounded to the nearest whatever when they're trailing zeros before the decimal point. So we'll say these numbers, if they're correctly rounded numbers, each have 2 significant digits. Representations here. Yeah, right. It's spelled at the same time. Significant digits in the numbers. And what happens is when you do correct rounding with multiplication and division, this doesn't count addition and subtraction, all right? But for multiplication and division and for our trig functions, if the numbers go in with 2 significant digits, we will round the output to 2 significant digits. The real rule is whichever number has the least significant digits going into all those calculations, we round to that many. So the least here is 2. So we're going to round this to 2. We'll say this is approximately equal. You don't have to use this approximately stuff. And I'll take the first 2 digits, and since the next digit is 2, I'll round it to just 25. And since we're doing the sides, the other sides are in degrees. This one is in degrees also, right? So the angle at the top is 25 degrees. That's all I can solve for immediately with the law of sines. But now I've got it, right? Because what I wanted was alpha with the idea of getting to theta. Now you use the sum of angles theorem. The 3 angles add up to 180 degrees, and I know 2 of them. So alpha, the last angle, is 180 minus the angle I was given of 73 degrees less the angle 25 degrees I just found. All right, let's see, this is 98. So I've got 82 degrees left, right? Well, if alpha is 82 degrees, then theta, being a complementary angle, is 90 minus 82, comes out to be 8 degrees. Here's the difference in subtracting and adding. When you subtract or add numbers with significant digits, what you do, and this one is exact, so you can carry it on forever if you want. What you do is when the first one runs out of significant digits, you round it right there. So you call this 8. So subtraction and addition is different. You round where the first one runs out of significant digits. Where multiplication and division and these trig functions, you carry as many as the fewest number going in. Fewest number of significant digits of the numbers going in. All right, so we'll say that's approximately 8 degrees. There it is. There's the tilt of the Leaning Tower of Pisa, but this is actually kind of deceptive if you know your history. Look on there on Wikipedia or something. It's kind of fun. The tower, the reason it tilts is not that they tried to build it crooked in the first place to make it an eyesore. They instead just built it, unfortunately, on unstable ground. And it, you build a tower on sand, it starts to tilt, and it started to tilt over the years, and eventually, it drew a lot of crowd. But it started to tilt so far that they got worried that it was instructional. Its instructional integrity was failing, so they straightened it up a little bit, but they didn't straighten it up all the way. Why didn't they straighten up all the way? I guess they lose all their tourism, must be. So it's not as tilted as it used to be at one time. They fixed it a little to make it still spectacular, but not going to fall down or something. So you can look on Wikipedia and see it. It's kind of fun looking that up. There's our first problem of an oblique triangle. This is the Leaning Tower. Let's look at another one. Here's a fun one. This is from Math is Fun, right? So it must be fun. Let's see, where is it? Yeah, there it is. They're going to give us a commercial at the same time. Let's see if we can get that partly off. There we go. No, it's not going to go away. All right. They're smarter than I am, apparently. All right. Here's the problem. There it is. Problem number 1. Oh, let me put it on the online here. All right. For those of you online, go to the Math is Fun website under Law of Sines problems, and you'll find 2 fire lookout stations are 15 miles apart, with station A directly east of station B. Both stations spot a fire. The angular direction of the fire from station B is north 52 degrees east, and the angular direction of the fire from station A is north 36 degrees west. How far is the fire from station A? You see what this is? This is a triangulation problem. I said at the beginning of the course. When you have a couple of spotting stations and you know the directions to the fire or the missing person or whatever it is, and you know the distance between the stations, you can solve the triangle and figure out exactly where the location is of what you need. All right. So the big hint on these kind of applied problems is first draw a picture. It'll often help you immensely. Let's draw this one, and we have to figure out what that kind of angle means. There's the picture. I can't get it to stop in the right spot. Here's the graph of what you draw, right? North 52 degrees east means turn 50 degrees east of north. North 36 degrees west means turn 36 degrees west of north. And you can also put south so many degrees east or west, right? But that's what it means. So the one lookout station here turns 36 degrees this way and sees the fire. The other station turns 52 degrees and sees the fire, and they know that they're 15 miles apart. How far is it is the question from this station, I'm sorry, station A, this one, to the fire, right? Then you can send the fire department out there to take care of it, right? And you can figure out the latitude and longitude if you need to from that. So let's see if we can solve that side of the triangle. Let me put this back on the board. So, example, a fire is at, the way it's drawn there at least, that sounds like backwards from what they said, I don't think so. North 36 degrees west from lookout station A. And also at north 52 degrees east from station B, which is directly east of A, directly west of A. But I guess they put it the other way, with A directly east of B is I think what they said. "15 miles between stations." How far is the station, or the fire from station A? All right, so we said the big hit on these things is to draw the picture first. Here's the sketch, what you saw on the overhead there, 15 miles here from north, if you draw north this way, and 15 miles east of B is A. Then I'll go 36 degrees west of north from here. Oops. So this must be 36 degrees. And from north here, 62 degrees east of north for that one. Then it's 15 here. What do I have? Well, I only have one measure, and the triangle is 15. So what I do, here's where the picture shines, right? Since east and north are 90 degrees apart, these are complementary angles. This one must be 90 minus 52 is 38 degrees. Here's why you want to draw the pictures to figure this kind of stuff out. This is 36 degrees here, and these two are complementary, add up to 90 degrees. So this one must be 54 degrees, right? So these add up to 90. Now I have angle, side, angle data, once I figure that out in the picture. So what I do, it's not side, angle, side, or side, side, side. For the law of cosines, it must be the law of sines, the one we're doing today. So we write down immediately what we know, and we want to write 3 numbers we know and 1 we don't. And what that entails generally is taking an angle and opposite side, and alas, in an angle, side, angle, I don't have an angle and opposite side, right? I've got the side between the 2 angles. So what am I going to do to get an angle and an opposite side?
Get the third angle.
There you go. Yeah, get the third angle. If I want to call this one, let's see, opposite A. Let's see, if we call this alpha here, call this beta in this corner, then this would be gamma. So we'll say I need to find gamma. Gamma is 180 less the other 2 angles, 38 and 54, whose measures add up to 92. So this must be 88 degrees. It's almost a right triangle, right? But it's not. So we have to use the law of sines rather than right triangle treatment. So there's the angle up here. Once I have an angle on the opposite side, now I'll use the law of sines, and I'll say sine of gamma, 88 degrees, is to its opposite side, 15, as, here's the one I wanted to find, its opposite beta, so I'll call it B. That's the one I want to find. It's a good idea to mark the one you want to find, too. As something is to B. Well, its opposite angle is 38 degrees, right? So a sine beta, 38 degrees, is to B. There it is, a trig relation relating 3 numbers I know and 1 I don't. So sometimes if you're given angle, side, angle, you want to find the last angle first. Whenever you know 2 angles, immediately find the third one. It's just a subtraction, right? And then do this where you need an angle on the opposite side in order to write 3 quantities you know and 1 you don't know. Now, there's multiple ways to solve this. The first one I'm going to say is one way to solve this. You can solve it by any algebra technique you want to get started. is to say if these two are equal, their reciprocals are equal, right? So I'll write equivalently 15 is to sine 88 degrees. And I should have put over here, this is 5 star, the law of sines, one of the three equations. 15 is to 88 degrees as the reciprocal of the other. Over on the other side, B is to sine 38 degrees. Boy, why didn't I just start with this instead? A is to sine alpha, as B is to sine beta, as C is to sine gamma. The answer I could have, and if you look in the library, all the different trig books, some of the books will put it this way, and some of the books will put it the way we did. Sine alpha is to A, as sine beta is to B, as sine gamma is to C. The fact is you can write the law of sines either way. It's just as good, right? The denominators are never zero in non-right triangles, and so you, or even in any triangle, right? Sine of 0 or 90 is 0, 0 and 180 is 0, so you're never going to get division by 0 here, and no side of a triangle is ever 0. So either one is just as good as the law of sines. So instead of writing this first with our law of sines in the book, you could just start right here using this law of sines. So sometimes you can save a step by using, just writing side is the sine of the angle, and side is the side of the angle. Nonetheless, we'll start with our original equation that we memorized and say in some of these triangles, it's easier to start with this one. Some of these, like this one, it's easier to start with this one. Now, in this one, we just have to multiply by 38 degrees and get 15 sine 38 degrees, multiplying the left by that number, is to sine 88. And B is on the right with the sine 38 degrees canceling. Simple computation on the calculator, right? The calculator then says, and here's a warning to you, okay? This is what a lot of students do. If you have an old clunky calculator like this one, it will put in the left parenthesis, but it won't put in the right. What if I forget to put a parenthesis right here? What's going to happen? When I do it on the calculator, I'll put 15 times sine, and it'll put in a parenthesis for me, 38. And then I'll put divided by sine 88. And on the TI 83 or 84, it will automatically close it here. And it'll put it in this parenthesis and close the second one. So if I don't put right parentheses, it'll close it here. And we'll take the sign of this whole thing as though it was a division like this, right? And that's not what you want. You want sine 38 degrees. So when you do these, make sure you close the parentheses. You've got a calculator that doesn't put 2 in. Lots of the new ones put 2 in anyway. Or they'll put a long bar here. If it shows the long bar or it shows 2 parentheses, then you're fine. But if it's like this one, where it puts a divide sign on the screen or it prints like this, then you want to make sure to close your parenthesis there. It will close it for you and not tell you anything. The idea is if you wanted sine 5 degrees, you don't have to close your parenthesis. It saves you a little time. You can leave it off and the calculator will do it for you. But it'll kill you on this one. It'll give you the wrong answer, right? You miss the fire, and the fire department will go the wrong way. So yeah, I'll tell you, there's a good story. I can't remember. I got to look it up sometime. One of those satellites they were shooting up many years ago when it was more difficult, actually, very expensive to send satellites up. Somebody made a trig error, forgot to convert between degrees and radians, and the rocket went astray and they had to blow it up and they lost the satellite. You got to be careful on this stuff for things for important issues like that. Make sure your calculator's in the right mode and you close your parenthesis here, right? Let's get rid of my advertisement here. I'm getting tired of it being a distraction. There we go. So B is this, make sure you close the parentheses. And it's not a bad idea to close it on these too. On the more expensive TI 89 or the Inspire with the computer algebra system, if you don't close it, it will complain. Unbalanced parentheses. That means you didn't put the same number of left as right. And then you'll know. But on the cheap calculators, not cheap. The basic calculators, they're not cheap. Some of them, if you don't close it, will close it automatically. You just have to be careful. All right, so let's try this one. 15 times, and make sure it's in degrees mode, sine 38 close divided by sine 88 close. We get 9.240 55, etc., etc. Where do we round this one? If these are rounded numbers going in, we don't necessarily assume that. In real life, these numbers, on the problems on the homework, they may just be assumed to be exact, and you can put however many decimals you want. But if it says use correct numbering, assuming that these were correctly rounded numbers, then once again, we carried two significant digits in each of these numbers that went in, and we're doing divisions and trig functions. So we're going to carry two significant digits on the way out. Here's the first non-zero digit. Here's the second. We're going to round this and say it's approximately 9.2. And since the other measure was in miles, this will be miles. And you tell the fire truck to drive 9.2 miles and at 36 degrees west of north, and hopefully we'll get to the fire quickly. There it is. All right, so you see these are kind of fun examples you can do. Now you can solve any triangle quickly instead of dropping perpendiculars everywhere like a lot of lazy engineers do when they haven't done their trig in a while. All right, engineers are very good. I'm not making fun of them. Let's try another one. We did angle side angle here, and we did side side angle, one of the cases. Let's do an angle side. Here's off your homework, number 1A. This will get you started. Hopefully, see if you get the same. If you have trouble getting the answer, maybe this will help. This time I'm going to say something else. I'm going to say solve the triangle. That means find all angles on all sides given these numbers, right? Suppose that alpha is 35 degrees, gamma is 73 degrees, and C is 20. Whatever, feet, let's say. It doesn't say on the handout. What does solve the triangle mean? It means find all angles on all sides. And what we'll always do in here is give you 3 measures because that's the minimum needed to solve it. And then we'll mean, since there's 3 angles and 3 sides, you have 3 more things to solve for. So you see the object here means find all 3 other measurements, angles and sides. Whatever's left, all right? And there's a hint here, you don't want to just use the law of sines 3 times, even though you could. Just like this last problem, if you get where you know 2 angles, instantly find the 3rd one, because it's just a subtraction and it's easier. Whenever you're solving and have 2 angles, don't use the law of sines again. Use the sum of angles theorem. When 2 angles are known, immediately find the 3rd. So an angle, again, draw the picture of the first order of business. So you try to draw it reasonably accurately, so you don't fool yourself. 35 degrees is a little over 1/3 of a right angle. There it is. And it goes up here. And then over here, gamma is 73 degrees. That's close to a right angle, so not real close, something like this maybe. And here's alpha. Here's gamma. So where does C go? 20 feet. Remember, if I use these letters, it's always assumed that C is opposite gamma. So 20 goes over this side. So draw that triangle, and now we know what we have to solve. Here's gamma and C. Here's alpha, so this must be A. And alpha and gamma here means this must be beta, and this must be B, opposite beta, right? So draw the whole triangle in, and now we know what we're doing. And now we'll write a trig relation that relates, well, first, since we're given 2 angles, we'll immediately use, so we're finding 3 items. Here's the first. We'll immediately use 180 minus the 2 we know is the remaining angle. 180 minus 35 minus 73. Let's see, these add up to 108. Right, that leaves 72 degrees to get to 180. So there's one thing immediately, and I should have said this is beta. We found beta, all right? Don't use the law of sines, it's longer and more mistake prone, right? 2, now we're stuck with the law of sines, though. We can use any angle on its opposite side that we know. So here's 73 degrees and 20 feet, let's use that. Sine, in fact, let's use the law of sines upside down. The side is the sine of 73 degrees, right? 20 is the sine of 73 degrees as, let's find side A. As A is the sine 35. And so we've written the original law of sines, the reciprocals, to save a little time here, because now all I have to do is multiply by sine 35 degrees, and I've got it, right? The left side multiplied by sine 35 is 20 sine 35 over sine 73 is A. Right? When I run that on the calculator, A comes out to be, again, make sure you close the parentheses here, 20 times sine 35 closed divided by sine 73 closed gives me 11.995. If I'm going to round to two digits like these are, we'll say it's 12. And it's the same units as this one, it has to be feet. Right? So that's 12 feet. I've got 1, 2, I've got one more to go, right? I'm missing one side. What is it? I'm missing B, I guess, huh? I've got C and A, so I'm missing B. So I'll write the relation for that. I'll say B is the sine beta, which beta was 72 degrees. And I use two of the things I know. I like to go back to the original thing, because if I use some of the later stuff unnecessarily, and I'm using rounded numbers obtained from rounded numbers, sometimes there's a slight more error in there. So I'll go back to the original numbers when I can, just to produce a tiny bit of rounding. You don't have to do that. It doesn't matter. Here's gamma and 70 and 20. C equals 20 opposite each other. So those are only rounded to, for the first, to put them in here. So I have now as 20 is the sine 73 degrees. There's one of the three laws of sines, again, star. This is step 3 to find B. Now I put the law of sines upside down again because it saves a step, right? I'll multiply by sine 72 degrees and get 20 equal, B equals 20 sine 72 degrees over sine 73 degrees. And now this tells me something about the final triangle too. One angle is 72, one angle is 73. This is almost an isosceles triangle, right? With two equal sides. So I should expect the two corresponding angles to be almost equal. When you're done, this is so complicated, you always want to check it like that, right? Let's try this. 20 times sine 72 closed divided by sine 73 closed rounds to 20, right? This gives me 19.89 something. We're going to round it off to 20, and to two digits, it actually looks like an isosceles triangle. So there it is. We're given three measures, and we find the other three. It's solved. We got to make one last recommendation. After you're solved, do a double check. There's so many complications here that it's easy to make a mistake. Draw the triangle, right? Go back on the original triangle and draw the other sides in. What we got is that B is also approximately 20, those two digits at least. And beta is 72 degrees. And let's see, what else do we get? A is 12 feet. Is that a reasonable triangle? Right? Here's what can happen. Suppose you get this triangle, and this is 3, and this is 4, and this is 9. What's wrong with that triangle? If this is what I solve for? Shortest distance between 2 points is a straight line. How can it be 9 here? But if I go around, it's only 7, right? So any two sides of the triangle have to add up to more than going one side. So you check all these. 12 plus the next shortest side, 20, is bigger than the remaining side, so that's okay, right? You check that the three angles, 35 and 72 and 73, add up to 180, and they do. And you check that the smallest side is opposite the smallest angle, next smallest side is opposite the next smallest angle, and the longest side opposite the longest angle. Those are things we know about triangles. I'll put those in next time when we have more time to look at this, because we're out of time. But we'll say always do a sanity check, as I call it. Check those three things that are easy. You just look at them and see if you made a big mistake somewhere. And sometimes you catch it like this, right? Here's what you want to do then for this homework. Look at section 8.1, all of them. However, the side-side angle ambiguous case, where you get 0 or 2 solutions kind of thing, we haven't covered yet. So side-side angle can wait on those when you're given two sides followed by an angle in that order. All right? Just section 8.1 on the law of sines, and I'll see you next time then. Thank you for your attendance.